In this section of Chapter 8, we'll talk about synthesis of alcohols, phenols, and ethers, and reaction of ethers. We begin with reaction of alkene. This is an alkene. We already know about this. This is Markovnikov's addition of H2O to alkene. This is a cyclic alkene. Now, you can think of H2O as HOH. Remember that H goes to that carbon that already has larger number of hydrogen. So let's fill in with hydrogen around the carbon-carbon double bond. So this particular carbon has one hydrogen. This carbon doesn't have any hydrogen. So obviously hydrogen would go to the carbon that already has hydrogen. So in other words, this bond is going to form with hydrogen, and obviously OH would go to the other end. So that means this particular end gets OH and this particular end gets H. So finally you end up with this product. This is one way of getting alcohol from alkene. The other way of getting alcohol from alkene would be by using basic potassium permanganate. Again, we also discussed that before. Potassium permanganate, this would be a syn addition in basic media, and which would eventually give you two OH group side by side. Since it's syn addition, if there is a cis trans possibility, you're going to get a cis product. You can also get alcohol by reduction of aldehyde and ketone. That's what we are showing you here with propanol. Propanol, Al, represents aldehyde. Sodium borohydride, it is going to provide H minus. Now many reactions you have seen that H plus takes part. In this case, H minus. H minus means there is a pair of electron on hydrogen. That's how sodium borohydride reacts. Sodium borohydride, when releases hydrogen as minus, that would be attracted to these carbons. It's good to have some understanding of it so that you do not forget it. So whenever H minus sees that positively charged carbon, is going to go over there. And as soon as hydrogen makes a bond, the carbon with delta plus would have too many bonds. So it has to get rid of its weaker pi bond. So it releases its electron onto oxygen, and oxygen then gets minus. So let me show you one intermediate step so that we can understand this reaction. C, 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 and let's keep this hydrogen intact. Then you'd have O minus. Make sure you understand why it's O minus, because that has now extra electrons and hydrogen gets bonded here. And if you fill in with electron, let's use a different pen. Hopefully we see it. 4, 6, 7. It's supposed to have 6 and it has 7, so it's minus. So we are right about that. And then from H3O plus, it grabs H plus. So H plus would be attached to that O minus, and you finally get this compound. So sodium borohydride changes a carbonyl group to OH group. So here I wrote down for you to study a little carefully. Aldehyde to 1 degree alcohol formation happens. And that's what we have seen here. This is 1 degree alcohol because this functional group, the carbon that holds that OH group is 1 degree because it's attached to one other carbon. This is one other carbon, so this is 1 degree. So aldehyde gives 1 degree alcohol. If you use ketone, you get 2 degree alcohol. But if there is, keep in mind, for carboxylic or ester, there is no reaction with sodium borohydride. So sodium borohydride only reacts with aldehyde and ketone because it's kind of a milder reduction agent. Lithium aluminum hydride works pretty much similarly as sodium borohydride. It provides H minus, but this is stronger than sodium borohydride. So in other words, it provides first H minus, just like sodium borohydride, first provides H minus, and let me show you that how it's worked. This is working on carboxylic acid. Since it's stronger than sodium borohydride, it can work on carboxylic acid, ester, and that's what you're going to see here. So this is carboxylic acid where H minus goes to that carbon which double bond. Now see, this is delta plus, this is minus. Of course, this oxygen with OH is also minus. So that's carbon would have fairly significant amount of positive charge. So H minus goes over there, and that breaks this bond. The weaker bond is released. So you are going to get, let me show you that what you are going to get in this process. This becomes O minus 2, 4, 6. That's O minus. This is OH. This is H. Then from the acid provided, with this lithium aluminum hydride, it gets bonded to oxygen. So we have basically two OH groups here. So now two OH group, you can get that this is going to form H2O and go away. So this would initially form CHO, and obviously double bond. This is aldehyde. Then from aldehyde, it works with another step. Remember, H minus is given by lithium aluminum hydride, and that goes to that carbon with positive charge, and that releases it onto oxygen, and eventually it forms CH2OH by adding H plus from H3O plus. Similarly, you can think of reaction of ester. This is ester, which is methyl pent 2NO8, and lithium aluminum hydride would give you this. Since hydrogen is released as H minus, let me remind you this, it's not going to be attracted to this carbon-carbon double bond. So in other words, carbon-carbon double bond would remain intact in this kind of reaction. Now let me go over one Grignard reaction that shows you how carbonyl compound is converted to an alcohol, and we go back and find out what reaction would provide you that particular alcohol. Now this is coming from the homework number 36, page 288. Let me first write down the reaction product so that we can think about it. CH3 CH OH, and then you have CH2 CH3. Now the question is, what Grignard reagent and what carbonyl compound you need to get this particular product. Basically, this would be your end result. Now the question is, how do I get it? By using Grignard reagent. Remember Grignard reagent, it would be something like this, RMGBr. This is an alkyl group or aryl group, and then that would react with a carbonyl group. So I'm just showing you what you'd be looking for. So you need to get MgBr plus a carbonyl. Now I think the best thing for you to go backward to form carbonyl out of this. This should be our thought process. Let me show you how this can happen. CH3, and I'm going to get rid of the hydrogen for the time being. See, I'm talking about the hydrogen with the carbon, which gets bonded to OH. So this is OH. Then you would have C, so that I can clearly see the bonding. Now what I'm suggesting is, since you need to have a one carbonyl group, so let's create one carbonyl group. So bring this electron pair in between so that I'm creating carbon double bond carbon. Then it has to get rid of either of these two. Either these two carbon or get rid of this carbon. Either one is going to happen. And both ways you can make this compound. So let's assume that I got rid of these. So now my carbonyl is going to be C, C, double bond O. Of course, I mean, it'd be less confusing if I stick in hydrogen here. It's aldehyde. Plus CC, this is the group I'm talking about, CCMGBr. So basically, these are the two components you're going to get. Let's double check. Now, this is plus, this is minus, so CC minus, this whole thing, will be attracted to this, and then this is going to form a single bond by releasing its electron pair onto oxygen. It will give you O minus, and then in presence of H3O plus, it gives you this product. So I can get this product by combining this aldehyde, CH3CHO, and CH3CH2 MGBr as Grignard reagent. Let's try another one, which would be good practice for you. Let's try part C. In part C, looks like it's a big formula, but it should be done very similarly, so you don't need to worry about anything. So just write down carbon and OH. This is the final product you need to end up with. This is the alcohol, and that's one benzene ring. There is a second benzene ring, and there is a third benzene ring. Okay. Actually, this double one should have been here. So these are double, single, double, single. So these are the three benzene rings and OH. Question is, how do you make this alcohol out of a carbonyl group and a Grignard reagent? Again, I'm trying to make a carbonyl group by pushing out one of these bonds. So I'm going backward to generate this carbonyl. So bring this electron pair in between carbon and oxygen, and that has to get rid of one of these bonds. So let's take it out. So now I can find out two fragments. One, C double bond O with two benzene ring. So you can see this double bond, single bonds, bond. And the other one will be on this side. Okay, so that's the other bond. So I got a carbonyl group. Now I would attach MgBr to this benzene. So it's going to be like this. MgBr. Always a good idea to double check, because this is going to be minus, Mg is going to be plus. So this minus would be attracted to this carbon, and then carbon is going to release electron pair onto oxygen, and that finally gives you the product that we are looking for. Okay, so this is how you can make or synthesize an alcohol by using a Grignard reagent and a carbonyl compound. This is Williamson ether synthesis. We have discussed this before. Here in this particular case, you have a 3-degree alcohol. In presence of sodium, it loses hydrogen and it forms alkoxide, this alkoxide. This alkoxide, oxygen is negative, so it's attracted to methyl group because of iodine there. So when it gets bonded to methyl group, it has to get rid of I minus so that it conserves its appropriate number of bonds. Oxygen would have 2 bonds and carbon would have 4 bonds. So you end up with this after iodine leaves. And also we know that iodine is a very good leaving group. so it leaves quite readily. So you get ether functional group here. Now we can synthesize phenol by a reaction like this. Sulfur trioxide in presence of sulfuric acid gives you sulfonic acid. So this is toluene, para-toluene, sulfonic acid. This is the sulfonic acid group. Once you have a sulfonic acid, then you use sodium hydroxide around 300 degrees centigrade, and in presence of an acid, you're going to add acid later on. First you treat it with sodium hydroxide. That's going to replace SO3H by OH, and then at the end you add H3O plus to neutralize that acid. So this is how you can get phenol. Now we're going to discuss about reaction of ether with HI. Now in this case you can see that this oxygen has a pair of electrons. So that pair of electron finds this hydrogen with positive charge, quite attractive. So it goes in there. And then hydrogen has to get rid of iodine because hydrogen can only have one bond. So that's how initial bonding takes place. So this is what you see here, OH. And then since hydrogen comes as a positive, so you have a positive charge there. There are two ways this reaction can happen. In SN2 type of reaction, it's a single step reaction that happens when intermediate is not a tertiary carbon. In this case, this is not tertiary, this is 2 degree. You can focus on this, and this is 1 degree. So in this kind of cases, you would have SN2 type of reaction. That means one group comes in, the other one group leaves at the same time. So in this particular case, iodine tries to avoid the bulky group. In this case, let me show you that this is not favored. This is the bulky group, 2 methyl group attached to that carbon. So iodine doesn't want to get there, rather it tries to avoid that crowd, and it wants to go here. So iodine would get bonded in here. So keep this in mind. In SN2 type of substitution reaction, iodine goes to that carbon with least number of substitution groups to avoid the bulky groups. Ether reaction can also happen in a different manner, especially if it involves a tertiary carbon. Like in this particular case, this carbon is tertiary because that carbon is bonded to 3 other carbon. Now why? Whenever there is a possibility of tertiary carbocation formation, it does form because tertiary carbocation is more stable than primary or secondary, or 1 degree or 2 degree. So basically, you first get the cleavage of this bond with the formation of carbocation, and then once carbocation forms, and you'd have Br gets attached like this, and then hydrogen goes to the other end. So you get this compound. Now these are the reactions. These are basically showing you cyclic ethers. One for dioxane having oxygen in part of the ring structure, tetrahydrofuran, 5-membered ring with oxygen. So, and how can we make it? Like if you begin with cyclohexene and react with peroxy acid, you can get something like this. It's not terribly important for exam, but now epoxides, again, this is the triangular ring structure with oxygen, and you can see that that ring structure is quite, it's a triangular structure, so it's a highly strained structure and opens up quite easily. And this reaction shows how it opens up and leads you other product formation. Again, this is the continuation of that ring opening structure where you end up with trans cyclohexane 1,2-diol. thiols and sulfides, they usually have bad odor and have the ending for thiols have SH instead of OH. OH is for alcohol. So keep that in mind. Thiols and sulfides both have similarities in that sense. Now sulfides, in this particular case, this looks like ether linkage, except that instead of oxygen we have sulfur now, and it's called methyl phenol sulfide. So reactions are very similar. Here you have, instead of oxygen, you have sulfur minus that reacts with methyl iodide, and methyl gets bonded there. So that's how you get the final product. Quite often protein structures are bonded to each other. Now sulfur is used as a bridge structure, and that's what we're showing you here. In presence of catalyst, it forms a link. I mean, one protein gets bonded to the other protein through sulfur linkage, and these are often called cross-linked protein.